So chapter 7. So when I look at a chemical equation, such as this one, what do I see in it? I see several things. First, compounds on the left of the arrow are usually called reactants. Compounds on the right of the chemical arrow or the reaction arrow will be products. That's number one. Number two, I see coefficients. So I see 2. When I don't write anything, that means it's 1. And I see 2 in front of H2O. The third thing, I see physical states. G for gas, L for liquid, S for solid, okay? And sometimes I see AQ. AQ means aqueous. Let me show you an example before I get into something else. Here's an example. So AQ, that means aqueous. So you got the solid, S, liquid, L, G, gas, and AQ, aqueous. So these are physical states, basically. All right. I may see some reactions where I see a little triangle on top of the arrow. What is that supposed to mean? It means heat. Heat. And anything up to the reaction arrow, including the arrow, will be reaction side, reactant side. Anything after the arrow will be product side. Product side. Okay. Sometime you will see an electric current written. So these are chemical equations. Very important that we are able to balance them. And balancing chemical equation is not really, doesn't have really rules. You always have to basically make sure that the number of elements on the left-hand side equal the number of the elements on the right-hand side, atoms of each element. So that's basically the deal when it comes to balancing chemical equations. So let me just open the worked file because it does have some examples of chemical equations. So this is chapter 7, once again. I want to make sure that I am sharing this the right. Yeah. So here's the worked file or the worked examples file in chapter 7. It's telling me indicate the number of each type of atom in the following balanced chemical equation. So if I look at the left-hand side, I see here Fe2S3 plus 6HCl, giving me 2FeCl3 plus 3H2S. What do I extract out of this? I extract that I have 2 atoms of iron, 2 atoms of iron. I have 3 atoms of sulfur, I have 3 atoms of sulfur. So I know that I have 3 atoms of sulfur. I have a coefficient that's 3 times S, so that's 3S. Hydrogen, I have 6 hydrogen. I have 3 times 2 hydrogen on the right-hand side. That's what we mean by balancing. We want to make sure that we have the correct number of atoms of that element on both sides of the equation. Cl, I have 6 of them. Cl, I have 2 times 3, so that's 6 on the right-hand side as well. Okay. Let's look at another example. I could leave this for you to figure out. So it's the same application of the previous example. So how many atoms you have of each element on each side of the equation. So you could figure that out. Now, how do I balance this equation? CH4 plus O2 giving me CO2 plus H2O. All right. Well, keep in mind that you may face to do more than one attempt until you are able to balance a chemical equation. And if you fail the first time, if you fail the second time, you shouldn't panic because there should be a set of coefficients that will allow you to balance that chemical equation. So start with the atom that appears once on that side of the equation. Like, for example, I have oxygen, oxygen. It appears in 2 compounds on that side. So I wouldn't start with oxygen then. I could start with either hydrogen or carbon. because carbon appears only once on this side, hydrogen appears only once on this side. So since I have 4 hydrogen here, maybe I can plug in 2 in front of H2O. If I do, then I'm going to have 2 times 2, so that's 4 hydrogen, and that 2 means I have now 2 oxygen plus 2, so that's 4. And if I have 4 oxygen on this side, that means I have to plug in 2 in front of the oxygen element on the left-hand side. Let's see, is that what they did? Yep. So you could see here that starting with an element that appears once on each side of the equation will make it easy on you, rather than starting with an element that appears more than once. Okay, so here's another example. So you have Al plus Cl2 giving me AlCl3. Okay, I have 1 aluminum, I have 2 chlorine, I have 3 chlorine. How am I going to balance this? Obviously, you're going to need to come up with a common factor. That will be 6. How do I make 6 chlorine on this side? Plug in 2. How do I make 6 chlorine on this side? I have to plug in a coefficient of 3 in front of Cl2. As a result, 2 aluminum, I have to plug in 2 in front of the other aluminum on the reactant side. Okay, the other hint I want to say, if you have a polyatomic ion, treat it as one unit. Don't treat the polyatomic ion as individual elements. Don't look at it as 1 phosphorus and 4 oxygen. Deal with it as 1 phosphate. So I have 1 phosphate, I have 2 phosphate. I have 3 sodium, I have 1 sodium. I have magnesium. So obviously this is an unbalanced equation. I'm going to need to balance. What do? You could start with any of these elements. Just make sure that you don't pick an element that appears more than once on that side of the equation. So you got Na3. I don't know, maybe you could plug in a 3 in front of the Na. But if you plug in a 3 in front of the NaCl, automatically that will force you to unbalance the chlorine, because the chlorine is going to have 3 chlorine on this side, 2 chlorine on the other side. So obviously 3 doesn't work. You need to think of something else. You have 2 phosphate here. You have 2 phosphate, but you have 1 phosphate. Maybe you could plug in a 2 in front of the Na3PO4. If you do that, that will basically have 6 sodium, 2 phosphate, and as a result, since I have 6 NaCl, that means I'm going to have to go back and put 3 in front of the MgCl2. Automatically, that is already balanced with the magnesium on that side. So it's a hit and try, and you realize at the end that, oh yeah, I came up with the coefficients that work to balance this chemical equation. So the bottom line, there is no really set of rules that I can highlight here to balance chemical equations, but what I can say, avoid balancing the atoms that appear more than once in each side of the equation. Deal with polyatomic ions as a unit. Don't deal with each polyatomic as individual atoms within them. And expect to basically do multiple attempts until you are able to successfully balance a chemical equation. Okay, so that's this part. This chapter also talks about solutions. Actually, there is a whole chapter about solutions, how to calculate constituents of solutions, so that will be covered there. But in order for you to just be familiar with at least some of the terms that you have, you're gonna read or come across in this chapter, just keep in mind solutions mean homogeneous mixtures. If you remember, we talked about matter divided into pure substance and a mixture of pure substances. And we said pure substance can be an element or a compound. And mixtures can be homogeneous or heterogeneous. Examples of homogeneous mixtures will be a solution. So solutions are homogeneous mixtures. If this solution has the main solvent being water, solutions can contain solvent, and a solute. If the solvent, oh, here it is. If the solvent is water, then we're dealing with an aqueous solution example. So the solute is usually the minor component. Solvent is usually the major component. So if I'm dealing with a solution where the minor component is solute and the major component is a solvent, and that solvent happen to be water, then it's an aqueous solution. What if the major component is alcohol and the minor component is solute, is water? Is that an aqueous solution? No, it cannot. Aqueous solutions have to have water as a solvent in order for them to be labeled aqueous solutions. Okay. Let's see. There is a type of reaction that is called precipitation reactions. These precipitation reactions, basically, they have a product, one product at least, that is a solid. Like in this case, you could see the mix of the two generates calcium carbonate, which happen to be solid. And when I see a chemical equation or an experiment done mixing reactants, giving me a product that is a solid, automatically I label that reaction a precipitation reaction, due to the fact that this solid would be called a precipitate. So that's where precipitation reaction usually happen, when you have a solid getting formed as a result of mixing reactants. Okay. This is another concept that's related to what we just talked about, precipitation reactions. Here's an example where you have calcium nitrate plus sodium carbonate, giving me calcium carbonate and sodium nitrate. I see aqueous mixed with aqueous, giving me a solid plus aqueous. Usually when I have ionic compounds thrown in water, which we just said, aqueous means water being a solvent, I will see them as ions. So you have calcium being calcium 2 plus, nitrate being NO3 minus, sodium carbonate, sodium being Na plus, carbonate being CO3 2 minus. But if it's a solid, you're not going to see that. You're going to see it stick together. You're not going to see it in the form of ions. NaNO3, you see it once again, Na plus and O3 minus. Those ions that appear on both sides of the equation, like in this case, NO3 minus on the reactant side, you see it also on the product side. Na plus on the reactant side, you see it also on the product side. These ions, we call them spectator ions, meaning ions that just stare at each other doing nothing. They don't cause formation of anything that's useful. However, calcium and carbonate, you see them, once they get mixed, they lead to the formation of a solid. That's why these two ions, calcium and CO3, they are not spectator ions. They are actually ions that lead to the formation of calcium carbonate. So when I see the net ionic equation, which means what was the major outcome of this equation, I will see the non-spectator ions being on the reactant side and what they led to. So you see here that this is like the summary equation of the full equation. So the full equation is what you see here. The detailed equation is basically what could be broken down to ions, and the net ionic equation is the summary equation. It tells me what really happened in this reaction. So you see here that you have a calcium plus carbonate leading to calcium carbonate solid. So that's basically a net ionic equation. Net ionic equation. Okay. Water solubility. So some solubility rules that are listed here. So somebody might ask, okay, how would I know that I need to predict this compound to be aqueous versus solid, versus liquid versus gas? Well, here's what I'm going to say. Compounds that are gaseous will be given to you. We will be told that they are gaseous. Compounds that are liquid, you will be told that they are liquids. So you will see that physical state listed in there. You're only going to be asked to provide whether it's aqueous or solid. And that will depend on this slide, slide number 33. Solubility rules. Solubility rules listed as you see here. The first rule, if the compound has an ammonium or group 1 metal or nitrate or acetate, automatically will be aqueous, will be soluble. So when the word aqueous means it's a soluble compound in water. The second rule, so like for example, ammonium chloride, sodium chloride, HNO3, acetic acid, sodium acetate, whatever chemical compound that has any of these, automatically you will be labeled AQ. The next rule, ionic compounds with the following ions are usually soluble, except, so halides are always soluble unless they are with silver or lead. So silver chloride, silver iodide, silver bromide, lead 2 chloride, lead 2 bromide, lead 2 iodide, these compounds are insoluble. They are solid compounds. That's the exception. Sulfates, they're always soluble, except if they come with barium and lead. Ionic compound, carbonate and phosphate and hydroxide, they're always insoluble, except if there is ammonium or group 1 with them. Sulfide, they're always insoluble, except if there is ammonium or group 1 or group 2 cations in those chemical formulas. So this solubility rules, it's very important for you to basically be familiar with in order for you to figure out whether the compound physical state is solid or liquid. Solid or aqueous. And you could see here that you will be asked, actually in some of the questions in the homework, you will be asked to predict whether it's aqueous or solid. So here's an example where we already dealt with those equations previously. Phosphate, sodium phosphate. I have a sodium group 1, so that's why it's aqueous. Halides, all halides except if there is silver or lead. This is magnesium, so it's aqueous. Phosphate, all phosphates are insoluble unless or phosphate are insoluble except if there is ammonium or group 1. Well, this is not ammonium or group 1, this is magnesium, so that's why it's a solid. So that's very important to be familiar with these rules. So once again, solubility rules on slide number 33. Please look at them.